So we're actually going to start with the syllabus. And I usually ask this question in my class: what does syllabus means? What is syllabus? Yes.
Sometimes might include a schedule of the homework.
Mm-hmm.
Includes like ratios, grades, what you would expect from us in class, etc.
Okay. All right. Anybody else wants to add to that? So what really syllabus? Yes, go ahead.
I was just going to say it's a general guide to the course.
Right. Anything else? I'm looking for one word, which to me defines what syllabus is. It's actually, my expectation from you, and also your expectation from me as well. So I would really, like for all of you to read the syllabus thoroughly. You'll be surprised how much time faculty, spend sending email, replying to student email, for which you can find answer in syllabus. So please read that thoroughly, and there's so much information in there. So I'm going to be, my name is Maksud Ali Mughal. You can call me Dr. Mughal or Professor Mughal, whatever you wish. I'm going to be, so we're going to meet Monday, Tuesday, Thursday, and Friday here between 12 and 12:50. For labs, we have actually 3 sessions, and all those sessions are on Wednesday. I'm pretty sure you would know what session you belongs to. So we got session DO1, which is 11 in the morning to 1:50, and then DO2 and DO3 in these times. My office hours are going to be Monday, Wednesday, and Thursday between 4 and 5 p.m. You can actually, usually I have I accept walk-ins if I'm not doing really anything or I'm not occupied, so I'll be more than happy to help then and there. In this course, there's a very good mix of different concentration in this class. There are RB, BME, and computer science and ECE, and it's really one of the basic foundation of understanding how digital systems work. So we really live in a digital world. We are surrounded by digital technology, starting from cell phones, laptops, Wi-Fi's, and all those. And all these are digital systems, and we just cannot imagine spending one day without it. So this is a very basic class which tells you why digital systems work on the principles of zeros and ones. When everything around is also analog in nature, why we prefer digital systems, and we'll learn about it, and we'll make machines, finite state machines in this class, which would basically be a computer. The first computer that came out was a basic calculator, right, which could do basic add and math. Okay, hopefully by the end of this term you should be able to make small computers, and that's what this course is about. I'm going to skip the objectives here, but I encourage you to read that. Now, moving on to the textbook. Textbook is optional because I take help from many resources, and I don't want to spend hundreds of dollars buying books when there's so much available already out there for free. However, if you wish to buy, they are mainly I'm going to be using these 2 books, Digital Design by Frank Wyatt, and the other one, Digital Electronics by William Cleats. Actually, for one of them, the second one, I found a link and I uploaded onto Canvas. Okay, you should be able to just go in there and then see what's in there. There are some electronic resources available. This one right here, the first one, you need to be connected to WPI network, and also I would actually require you to give me a feedback whether this link is working or not. And this basically, WPI is subscribed to Access Engineering, which give us access to many engineering books. So you can just go in search engine, just type digital electronics, and many books will show up. So try to go to some of those books and see if those are accessible to you or not, and then give me a feedback. And there's some other resources available which are very good, and you'll find many good examples and lessons there. Supplies. So this is probably the best investment that you would do. Next 7 weeks, this is going to be really helpful for you. It's just a digital template stencil with bunch of gates and inverters and bubbles. So this will make your notes look good. I usually encourage my students to, this was actually not a part of the syllabus, but I added it this time because I thought this is going to be good. So I usually use this Pilot Razor, different color pens. You can use just different pens. I'm going to be providing you the supporting material. So every morning, every time you come in, you walk in, I'm going to put my supporting material at the back on the bench. You pick one and then you walk down to your seats. And I'm going to be printing on both sides. So make sure you use something that doesn't leave a impression on the back page. Do you know, I usually give syllabus in a hard copy form, but this is such a big class, I decided not to do it this time. When you graduate, and according to one research, when you graduate out of school, you have actually consumed 2 trees in paper supplies when you are going to engineering school. So I'm going to be printing on both sides of the paper, and a binder and a folder, which you might already have. That would be nice, you can keep. So if you just keep good notes in my class, and you'll see, you will have an idea from first few lecture like how the supporting material is going to be. And if you can just attach them together and then put them in the folder, basically it will be a good notes for you, and then it will help you for your homeworks and exams and things like that. We have 3 exams scheduled: March 29, April 12th, and April 30th. So homework is going to be 20%, labs are going to be 20%, project is 10%, exams are 45%, that should be 15% each, and then quiz is going to be 5%. Okay, let's look into some more details. So the homework, there are going to be a total of 6 homeworks. Every Friday I'm going to assign you a homework, and that will be due the following Friday. Okay, how many of you have the ECE mailbox number? Okay, so probably the first thing you want to do when you walk out, maybe go to EC office. I think it's 209, and then either ask Miss Colleen or Deb to get you the email box number. Okay, submit your homework to the EC main office. In the main office, when you walk in, you'll see a box with the label EC 2029. So just leave your homework in that box. By Friday 4 p.m., your homework, which will be graded and will be returned by your EC mailbox by Tuesday 5 p.m. No late homework will be accepted. Please understand that you have 7 days to finish your homework, and Friday, when you submit your homework at 4 o'clock, around 5 o'clock before I leave my office, I'm going to upload the solution for that. And since I'll be sharing solutions for the homework, I cannot accept late homeworks. Okay, but things happen, this is life. If you have a genuine reason, reach out to me 2 days before or something. Okay, let me know in advance. 3 exams, 15% each. A single makeup exam will be offered for students with a genuine excuse. Inform the instructor at least 1 week in advance. However, this makeup exam will be comprehensive. That will mean that it will cover everything that we have covered in the class, in the term, and this will be at the end of the term. Okay. Now for the labs, there will be 5 laboratory experiments. This week we don't have any lab. Okay. We won't be able to cover enough content that you would be ready for the labs, but next week we'll start our lab, and this is the Basis 3 board that you will need. Okay, this is the FPGA board, Field Programmable Gate Array, Basis 3. It's made by Digilent. I think it's $180, and because you will be doing the labs in a group of 2s, so not everyone has to buy it. You can find your lab partner and maybe you can share the cost. Okay, so or maybe who has taken this class in the past, maybe you can get from them. Your labs are going to be pass or fail. Okay, so when you walk in, most labs will have pre-labs. That means you have to do the pre-lab once you walk into the lab. Okay, once you walk in, you submit your pre-lab to the TAs, or they would come over and sign off the sheet. If you do not do the pre-lab, you will not get the credit for it. The reason of doing the pre-lab is because we have a lot of students in the lab, and then we have limited resources to help. Okay, we want you to do well in your labs, just to provide you a good understanding, good basics. Doing pre-lab will help you, and you can finish the lab in maybe in less than 3 hours. So your lab grades will be pass or fail. Pass for successful completion of the entire lab during the assigned time slot or outside the assigned time but signed off by a TA within the week. So say you have a lab, you were not able, for some reason something went wrong, you were not able to finish the lab, you will have the whole week to finish the lab during the help sessions. We would have help sessions every day from 4 to 6. You can go and get help from the TAs during those help sessions and finish your lab. And the following week the report will be due. There's no formal report, but what report is basically whatever the project that you would make, project file, you just upload that file onto your Canvas, okay? More details will be available on Canvas under the assignment module. Pre-labs have to be completed before starting the new lab project, so bring the completed pre-lab work to lab session for TA to sign off. TAs will be in AK207 during help sessions. And yeah, very important. I have actually given away 5 or 7 micro USB cables. People bring their board, but they forget to bring their micro USB cable, okay? So even though I usually keep few extras in reserve, but please don't forget to buy this USB micro cable. Actually, if you have a Samsung phone, that data cable would work also. Quizzes. There will be 4 short quizzes in class during the week when there's no exam. I reserve the right to take the quiz on any class day. It is an alternate way for me to check the attendance, okay? The quiz will be open book, open lecture notes. You can use your notes to do the quiz. And those are going to be in the first 5 minutes of the class, okay? So try to come in early. This is a very fast-paced class, and if you don't come in early and you come late, it's going to be very hard to follow up, okay? Again, each quizzes will be digitally graded. Basically, you get either 0 or 1, and this will account for 5% of your final grade. And there will be no makeup for the quiz. Quiz takes place in the first 5 minutes of the class. Here is a course content and a timeline, whatever we would do in this course. So labs are here, Wednesdays. Homework, 1 due, 22nd Feb, March, and then so on. The first exam is going to be 29 March. So this is a good way of tracking like what's going to happen in this entire course. Okay, all right, I already talked about the EC mailbox, course policies. Just go through it. Any question that you may have so far, whatever we have covered. Do we have a question at the back? Yeah, thanks for picking that error. Yeah, it should be 12 to 12:50. Yeah, sorry about that. Yeah, I'll make that change. So, and I'm still trying to get in touch with all my TAs. Actually, there are 6 or 7 of them. We are trying to make a schedule for you guys. So this is what it looks like for now. But we will actually finalize it by Tuesday, tomorrow. I'm meeting with them tomorrow. So between 4 and 6, we will have these help sessions Monday, Tuesday, Wednesday, Thursday, and Friday. And these are people who will be there for you to help. Okay. So make use of these help sessions. Anything else, guys? Here's the email address of those people also. You want to make sure you keep them happy because there's a very good chance you might end up getting an A grade if you keep them happy. Yeah. Yes. No use of electronics. No cell phones, no laptops, nothing. You can bring hard copy, whatever you want to. Yeah. Anything else, guys? Okay. All right. So you guys gave your introduction. Let me just give a little bit of my introduction. I did electronics engineering in 2008, and I did my master's in industrial management and environmental sciences from Arkansas State University, and I did my PhD in semiconductor physics also from Arkansas State University, and I graduated in 2015. I joined WPI last year So I'm fairly new. Before that, I was working at Fitchburg State University. Does anyone know where Fitchburg State University is? Those of you who are in New Hampshire, it's pretty close to New Hampshire. And then before working for Fitchburg State University, I was at Arkansas State University for 1 year as an instructor. I do a little bit of research. I work on thin film solar cells. What it is basically you take a very thin layer of a p-type material, which is an absorber layer, and then you take another very thin layer of a buffer layer, which is an n-type material. You make a sandwich, join them together, and it makes a junction, and then it makes a very good solar cell. So we're using very tiny amount of material. We're looking at the nanometers. I do a little bit of high altitude balloon project, which is basically releasing the balloon in the air in the stratosphere. We're talking about 60,000 meters above the sea level, and we want to measure the CO2 emission. We want to measure the environmental pollution in the air. So we're looking at different greenhouse gas emissions and their concentrations. And then I do also a little bit of 3D printed electronics, especially drones for military applications or fighting applications. So anyone of you might be interested in knowing more, feel free to come, or want to voluntarily work on any of these projects, please. Okay, all right. What is a signal? Anybody? In an engineering terminology, what is yes?
It could be like a voltage that, like an impulse.
Okay.
That that can be produced through pressing the buttons or whatever.
Correct. Okay. Anyone else? What is a signal? Yes.
Anything that can carry information.
Correct. Good. Anyone else? Okay. All right. So a signal is a function that represents the variation of a physical quantity, which is mainly going to be either voltage or current. Okay. With respect to a parameter that could be time or distance. Okay, so most things that exist surrounding us are analog in nature. Let it be temperature sensor, pressure sensor, CO2 emission sensor, any kind of sensor. They actually work on the analog signals, okay, which is basically a varying voltage over a period of time. Okay, now why do we need to convert that analog signal into a digital signal? Why? Come on. No one? Yes, Hunter.
Because you can't really put an analog signal to a computer or like an online application.
Correct. Anyone else? Someone raised hand from here. Yes.
Analog signals tend not last as long as digital signals in a lot of cases, and they're a bit harder to transfer.
Correct. Both were good definitions. Yes.
It's easier to interpret data with digital signals.
Correct. So just like we use a common language and using which we understand each other, there's no other way for us to communicate with our digital systems, our microprocessor, microcontroller, unless giving them a sequence of zeros and ones, which is basically our digital signal, right? So we have to convert our analog signals into the digital signals, and our microcontrollers and microprocessors can do some intelligent decision making on that data and interpret those things into something which is useful to us. Okay, so we have analog to digital converter, which takes the analog data, convert it into digital, it goes into the computer, process it, and then that data, which is a sequence of zeros and ones, convert it back into analog, so we as human being can understand. It's kind of like a decimal number system. We understand 1, 2, 3, 4, 5, 6. We understand there's 9 between 8 and 10. But the computer doesn't understand that. Computer understands the binary formation of those decimal numbers. Okay, so we have to convert things into binary so that computers can process the information. And again, this is the output that we see as human beings coming out of any generic system. This is actually the temperature versus time. Okay, temperature taking at different times during the day, and you see it's actually analog in nature. It's being taken continuously over a period of time, and it's useful for us to and it's got two scales, vertical scales, one on the degree Fahrenheit, the other one on the right tells you in a degree centigrade. So it's a lot more useful for us. So I was actually working on this temperature sensor this morning, and I took a screenshot of it. So it has 6 pins, you can see the 3 pins here, and then there are 3 pins on the other side, and the product information that this actually has an accuracy range of plus minus 0.5 degrees centigrade. Maximum temperature it can measure is 125, and the minimum it's minus 40 degrees centigrade, also used for aerospace applications. The supply voltage would be 3.6 volt maximum, and it can take minimum voltage of 1.4. This is a data sheet IQ, which is basically a cosine current and versus temperature scale graph. And what you conclude from these two lines here, one in red, one in black. The black is when you are supplying 3.6 volt to this chip, and the red one is when you're supplying 1.4 volt to the chip. What do you conclude just looking at this graph right here? Yes.
In order for the 3.6 volt supply to work at the same temperature as the supply microcurrent.
Okay. All right. Anybody else? What we see and we can conclude from this graph is actually, as you see, as the temperature is increasing, the current, the cosine current, is also increasing. So say you have a sum module which is actually displaying a temperature which is 80 degrees centigrade. That means that chip is drawing how much current? At 80 degrees centigrade, if the supply is 3.6 volt, that chip is actually drawing 8 microamps of current. Okay, so if I go back to the definition of the signal, a signal is a function that represents the variation of the physical quantity, and in that case, what was the variation? It was the change in current, right, with respect to a parameter which was time. Okay, and this is how most sensors work. Okay, now the problem here is, say the temperature is 60, the outside temperature is 80 degrees centigrade, and the supply voltage 3.6 volt is drawing 8 microamps of current. How does computer understand that 8 microampere corresponds to a temperature of 80 degrees centigrade? Okay, we'll see that. Here's a generic system model here. Analog input, those are mostly going to be sensors. Any kind of sensor is going to give you analog input, usually in the range from 0 to 5, but some are which are low power mode that you will use for some of your microcontrollers. They'll go from 0 to 3.3 volts. Okay, what are the digital inputs here? Digital input are those which are going to generate logic 0 or 1. So you can think of switch. Switch can either be 0, on or off, right? So if when it's off, it's 0 volt. When it's on, it's 5 volt, right? Or can anybody name another digital input? Push button, right? Those kinds, okay? So analog input always goes to a transducer, which is an analog to digital converter here. That voltage, say 8 microamps or 3.3 volt, that is going to be converted in a sequence of zeros and ones, which then goes into a digital processing unit. It makes a smart decisions for us, and then convert the data back into the analog form, and then produce at the analog output. So most cars, they still have the odometer where you see the speed in analog, right? I know some of the model they have the speed in analog and digital both, but still, even though we are living in the digital world, the speedometer is still analog in nature. And then digital output could be 7-segment displays, right? And we'll see that. We'll do more of it in the future classes. Also, I wanted to show you one more thing right here. Okay, say there is another temperature sensor, and it's a 16-pin sensor. So this is pin 1, 2. Usually when you see a notch, this is where the pin 1 is. 7 is connected to the ground, 8 and 14. Okay, and this is your analog output right here, pin number 8. And this is just some sensor. I'm just making it up just for the sake of the explanation. And it's actually taking the voltage versus time. And you see this graph, the T0, T1, T2, T3, T4. These were the 4 different time periods at which the data was taken. So what is the voltage at T0 right here? So using this, we are trying to explain like how we are going to convert this analog data, which is a varying voltage, into a sequence of zeros and ones, which is understandable to the machine, the computers. So at T0, looks like the voltage is 0. At T1, around 1.5 volt, and T4 is about 5 volt there, right? Okay, now before I explain like how we can convert those numbers into digital, say you got 2 switches, switch 1 and switch 0, and looks like those are open. Okay, they're not connected, so whatever the voltage over here will not be able to go past through it because it's open, right? So right now it's actually 0 volt, or you can say it's off, correct? And similarly over here, 0 volts, or it's off. Okay, with this 2 switches, how many possible combinations we can have? I think you're done for today. Anybody else? Okay, yes, 4, right? Either both switches are off, either both switches are on, or this one is off, this one is on, and this one is on, and this one is off. So let me put it down over here. For a 2-bit system, you can think of these switch 1 and switch 0 as a 2-bit system. Okay, so switch 1 and switch 0 right here, either both are off or one of them is on. 1 would be on and 0 would be off. This one is on, this one is 0, and this one is 1. Both are on actually. Okay, so what would be a resolution for a 2-bit system considering the supply voltage is 5 volt, which was over here? Okay, so I have resolution is actually a ratio of supply voltage over number of levels. Okay, supply voltage is here is what, 5 volt. Okay, and how many levels do we have for 2 switches? We have how many combinations do we have? 4, right? Okay, which is basically 2 to the power 2. Okay, where 2 is basically is the number of bits, and because it's a 2-bit system, so 2 to the power 2 would be equals to 4. So if you do the math, you actually get 1.25 volt here. Okay, so that's the resolution we are looking for in a 2-bit system. Now this is not going to be the most accurate system because it only has 2 bits. If you look at your computer, we are actually moving towards 16-bit, 32-bit system. So we are talking about so many levels. In this, we only have 4 levels. So what does this 00 means in a digital system? This 00 is basically what? 0 volts, which is the T0, correct? Okay, what does this 0 level, next level tells you? It jumps from 0 to 1.25 volt this time, right? And this corresponds to the voltage at T1. Okay, 10, this corresponds to a voltage of 1.25 plus 1.25 would be 2.5, correct? 2.5 volt, and that's the voltage at T2. And then similarly at 1, okay, 2.5 plus 1.25, because that's the smallest increase, 3.75 volts. This will be at T3, okay, correct? So now what our computer understands here, when the voltage is 0 volt, it thinks of 0 0 in a 2-bit system. Okay. Now if the voltage is 1.5 volt, what would computer would think? Obviously it's going to think 0 1, but 0 1 corresponds to what? To a voltage of 1.25, whereas it should be the accurate voltage was how much? The accurate voltage was 1.5, whereas the computer would think it's 1.25, because because we only have 2 bits, so we have 4 number of levels, so the resolution is 1.25. So it's going to tell you that the temperature is actually, whatever the temperature is, it's going to be less than that temperature, because it's not going to the original value for that analog number. How can I get close to 1.5? What is a way for me to get close to 1.5? Yes? Have more divisions. So say if I change the number of levels, if I use 3-bit system, so that would mean 3 bits. So 5 volt divided by 8. So that would mean the resolution is going to be 0.625 volt. So instead of having an increment of 1.25 going from one level to the another, now I'm going to have an increment of 0.625 going from one level to another level. Correct? And if you do the math here, you'll get pretty close to 1.5. And if you keep on increasing the number of bits, you'll get to exactly 1.5. Okay? So this is how the computer understands what 0 0 or 0 1 or 1 0 or 1 1 means. Okay? So I thought this would be a good explanation. We'll actually explore more on this. Okay, all right. How are we doing on time? Okay, all right. So digital signals, we know that they can either be 0 or 1, high or low, 0 volt or 5 volt, on or off, true or false. There is nothing in between. Analog signal, they are analog in nature. You see the amplitude, which is the highest positive peak, and then one complete oscillation, which is basically the positive half and the negative half wave. This one complete oscillation, and which is referred to as a time period. And we know frequency is a reciprocal of time period. Some basic stuff about the analog signal. Maybe, well, it could be 0, it could be 0.1, it could be 1.1, it could be 5. You know, as you see, as it goes on the x-axis, we got time. On the y-axis, we got voltage. As time increases, the voltage goes to the maximum value and then goes back to 0, and then it reaches its negative peak value and then goes back to 0. So maybe it could be anywhere between 0 and 5, depending upon what time we're looking at. It's continuous in nature, it's continuously changing, whereas digital, it's actually 5 volt for a period of time, then goes 0 and then stays 0. So there's a straight line to it, straight line behavior. And like I said, it could be anything between 0 to 5. On and off, well, it could be off here, it could be on, but there's so much between 0 and 5 which we don't know whether it's going to be on and off. There's another lecture about it. We'll understand like how far we need to go above 0 that it will be considered as low, and how far below we need to be 5 volt that it will be considered as on. It varies from chip to chip and the material that was used to fabricate the chip. Any system can actually take any means. So it could be analog or digital, or it can be a combination of both. Here's an example of the analog, some electronic devices which have taken both forms. On the top you see the analog. You got voltmeter and you got these joysticks, and similarly the digital clock and digital multimeter. If I ask you which one is better, analog is better or digital is better, what would be your answer? Yes, yes. Yeah, it's really hard to give a definite answer to it because it may depend upon the application. But for most of the application that we use, we feel that digital systems are more accurate because they just provide more information. For example, the latest cars that we have now, they actually tell you the flow in, the flow out, how much miles you can drive in the given fuel that you have, and so much other information. Whereas the in the older car, we only had that one needle that would say empty and full, and then there's one scale in the middle. Or even with this analog clock, you see if the if it's between 4 and 3, you really don't know if it's 3.5 or 3.6 or whatever. So with digital, you get more precision. The bandwidth of the digital system is also very small. So say you're only looking at 0 to 5 volts. So you're not really going to look at more than above that. Also, the digital systems can be encrypted, so they are more secure than analog systems. Similarly, with the with this voltmeter, you get more precision. Whereas it's really you're going to have to do your judgment, approximation, trying to get to the closest value that you get. But with the digital system, you get more precision and more. And the more, they only have one decimal point looks like. But if you have more decimal points, you can actually increase the number of bits, and they'll give you more precision. I have a thermometer. It's a baby thermometer that we use for our daughter. And it only has one bit on the other side of the radix, of the decimal point. So it will tell you like 98.6, 101.1, something like that. But it will not show you the second decimal digit. Does anyone know how in old days, like these tape recorders used to work? So the way it would work, you would use a mic or something. You use your voice that will basically create the voice signal. And those voice signal, those sound waves will actually generate some pulses, okay? Kind of like an EKG report that you see. And those pulses will actually create a voltage, okay? And that voice is going to be laid down on that magnetic tape, which was made of some electromagnetic material, which would actually can be used. So sound signals are converted into electrical signals. Those electrical signals can go through the amplifier, can be processed, and then thrown to the speaker. And then, so you take a sound energy, convert it into electrical energy, and then electrical energy is converted back into sound energy through speakers. So this is how it used to work. In a digital system, for example, if you have those MP3 CDs, songs, if you see at the back of the CD, it might say something like that, 44,000 samples per second. So what digital systems are doing, they are actually basically recording data 44,000 times. They're taking 44,000 readings every second of the music and then just playing it, okay? So those numbers, those 44,000 numbers are then interpreted to a digital system where those numbers are converted into some voltage which approximates the original music at which it was played. So this is how it works. It really is, the varying voltage or current over a period of time, which does magic depending upon the material. The next example of the digital analog system. The one at the top is the analog. So this is the water tank level detector. As the water level goes down, you have this resistor. The resistance also goes down. And we're basically just implying Ohm's law. If the resistance is going to be smaller, the current is going to be larger. So at the analog output, you'll see the ammeter needle going towards the right because it's increasing as the resistance goes down. Over here, it pretty much does the same thing. It is taking that analog input and then doing that, implying that Ohm's law here, and then converting that data. Say it was generating some 50 milliamps. 50 milliamps would correspond to 10001111 in an 8-bit system. The computer digital system takes that data, does manipulate it, and calculates the flow in, flow out, and tells you a bunch of other things, and then displayed onto the output, which could be a monitor or a 7-segment display, LCD screen, things like that. We'll do a bunch of examples in this course that will give you more idea about these things. Television sets, you see the resolution is improving. There's like millions and millions of pixels on a screen. You can actually generate those pixels by digital logics, okay? And in most TVs, it is actually created using a certain bit number system for red, green, and blue. These are the primary colors, right? So this is the 8-bit system. For an 8-bit system, you can go from 0 to 255. And if the 8-bit system, all 8 individual bits for red, green, and blue are set to 255, it's actually going to create white color, okay? So imagine you have a TV screen, it's got million pixels, each pixel representing this data right here. So if it's 255, 255, 255, that pixel is going to generate white color among the 16 million more pixels that you have. Okay, so let's look at green. 0, 255, 0. If you look at it, red is set to 0, blue is set to 0, green is 255, so it's going to generate green color. And then changing these values, you know, you can get thousands and thousands of shades of green. Okay. Also, in a digital system, the single most, I'm using a biology term here, the single most atomic unit in a digital system is actually a bit, which is actually derived from binary digit. So it can either be 0 or 1. By placing them side by side, we can create binary codes. So why digital designs? Why digital design, guys? Whatever we have covered so far, what do you think of digital design now? Why do we need to do that? Yes. I think you're also done for today. Anybody else? Come on, this is gonna be, you know, I need class participation. I want you to enjoy and have fun, and don't be scared. Yeah. Yeah, great. Anybody else? What else you could think of? Yes. Yeah, go ahead. Right, that is also right, correct. Anybody else? Yes, go ahead. Right, analog system may have a lot of noise. So for example, at 80, we were looking at one graph where at 80 degrees centigrade, the temperature, the current was how much? 80 microamps, right? 8 microamps. Say it has a noise of 0.25 microamps. So it will actually give us 8.25 microamps and not 8 microamps. In a digital system, there's a way for us, and we'll talk about that, how we do that. There's a method we can cut down that extra 0.25 microamps to eliminate the noise. Okay, so that's one advantage. The data is stored in binary bits, bytes, and words, and these goes to files, and file goes to folders, and then folders to disk. Better devices, sound recorders, cameras, cars, cell phones, medical devices. Really, it's a digital world under the analog, and video games and PDAs these days. Digital design are accurate, use less bandwidth, they are noise eliminator, and various other advantages. So that was it. How do you generate a digital signal? Now there are different ways of generating a digital signal. You can actually use a switch, turn on and off to create a digital signal. You can use a push button to generate a digital signal. But in most of the electronics or semiconductor devices, we actually use BJTs, bipolar junction transistors, or MOSFET, metal oxide semiconductor field effect transistors. Okay. Now what's the reason? Because our push buttons and the switches, those are mechanical devices. Okay, so when we use a push button, let's say when we press a push button, this logic is supposed to go from 0 to 1, right? When I press the push button, this logic is supposed to go from 0 to 1. But what happens when I press the push button, it actually goes to the 1, like goes to the on, and then bounce off back because of the mechanical nature of the push button, and it fluctuates between 0 and 5 volts multiple times before it stabilizes. Okay, now for example, if you're creating a digital system for, let's say, military applications, and some missile comes in and you have to shoot that, target that, and you're slightly off by a few milliseconds, you're going to miss the target, right? So how do we avoid that? We use metal oxide semiconductor MOSFETs, field effect transistors. What basically it is, if you look at the you got the drain here, you got source. Right now the gate is attached to drain and source, so it's actually basically giving a route for electrons to flow in this direction. So it's actually creating a logic which is 1 here, correct? If I have the gate which is not connected to drain and source, the electrons do not have the route to go to the source, so basically we're creating 0 logic. Okay. This is the slide that I'm actually gonna keep bringing every now and then. This is really what we are going to do in this class. From transistors, transistors are built from semiconductors, silicon, different compounds of gallium arsenide, phosphorus, indium. They are used to make transistors. Using transistor, we are going to create logic gates, AND gate, OR gate, XNOR, exclusive NOR, and those gates then be used to create logic functions, okay, which have some kind of application. Once we have those logic functions, we can create flip-flop. Flip-flop could be used to store a bit, 0 or 1, and then using those flip-flops, we are going to create counters and sequencers, and using that we can create microprocessors, and when we have microprocessors, we can put everything together and make computers, okay. So that is our end goal, making finite state machines following this. So I'm going to keep on bringing this slide from time to time just to show how the flow is going. With this, I'm going to finish my lecture for today, and I'll see you guys tomorrow. So enjoy your rest of the day.